Rates of change. Suppose that y is a function of x, i.e. y equals f of x. Now suppose that x is a function of t. It follows that y is also a function of t. The chain rule, which was explained in activity 12.3, so the chain rule can be seen in a previous video, gives the formula dy dt equals dy dx multiplied by dx dt. Thus, the rate of change of y is related to the rate of change of x. We will use this idea to solve some real-life problems. The cost of extracting t tons of ore from a copper mine is C equals F of t euros, i.e., that is, the cost of extraction is a function of the amount of ore mined. Question 1. Explain the meaning of f prime t, the derivative of f of t. F prime t, so the derivative of f of t, is the rate of change of C, which is the cost, with respect to the amount of ore mined. For example, if f prime 3000 equals 500, this means that when 3000 tons has been mined, the cost of mining the next ton of ore will be €500. Question 2. What are the units of measurement for f prime t, the derivative? So the units of measurement are euros per ton, because the cost of extracting t tons of ore from a copper mine is C equals F of t euros. So euros per ton, that's the unit of measurement. Differentiate y equals 3x plus 1 cubed using the chain rule. So we're going to let u equals 3x plus 1, so that's the inside the brackets. And du dx is 3. So we differentiate inside the brackets. So the derivative of 3x, we just cancel out the x, we get 3. And the derivative of 1, we get 0. So the derivative of this is 3. Now we let y equal u to the power of 3. So that's the outside. So if this is u, then y is equal to u to the power of 3. So y equals u to the power of 3. And then dy du, so the derivative of this, we bring the power down in front, we bring the 3 down in front, and we reduce the power by 1. 3 minus 1 is 2. So the derivative of this is 3u squared. So we just differentiated the outside, we just differentiated the power. So now we use the chain rule. So dy dx is equal to dy du multiplied by du dx. So dy du is the derivative of the outside. And the derivative of the outside is 3u squared. So we put 3u squared inside brackets. And then that dot there means multiply, so we multiply it by du dx. And du dx is the derivative of the inside. And the inside is what's in yellow, and the derivative of that was 3. So the derivative of the inside. So we put 3 with brackets around it. Then we multiply. 3 times 3 is 9, so we have 9u squared. And now we swap back the u for what we let u equal to, which was 3x plus 1. That's what's inside. So we swap that back for 3x plus 1. So dy dx, the derivative of this, is 9 times 3x plus 1 squared. So this is the same question as the previous slide, it's just done in a slightly different way. So we have y equals 3x plus 1 to the power of 3. So this is the inside and this is the outside. So y prime, the derivative, is differentiate the outside multiplied by differentiate the inside. So this is the chain rule. So let's differentiate the outside. So we bring the 3 down in front, we bring the power down in front, and we reduce the power by 1. 3 minus 1 is 2. But we keep what's already on the inside. So we keep this. So we brought the 3 down in front, so the 3 came here. We kept what was inside the brackets, and we reduced the power by 1. Then we differentiate the inside. So differentiating 3x plus 1, we just get 3. And then we multiply 3, multiplied by 3 is 9. So we get 9 times 3x plus 1 squared, which is the same answer as before. The difference with this is that we're not using the formula and we're not using u. So we're just using the basic idea that for the chain rule, we differentiate the outside and we multiply that by the derivative of the inside. And then we put them back together. The area of a healing wound is given by A equals pi r squared. So this is the formula for the area of a circle. So let's imagine this is a wound and it's in the shape of a circle and it is healing, where r is the radius length of the wound. So the radius is a line that goes from the center to the edge, and we're labeling it as r. So this is the radius of the circle. So r is the radius length of the wound. If the radius length is decreasing at a rate of 0.5 millimeters per day, how fast is the area decreasing at the instant when the radius length is 10 millimeters? So this wound is getting smaller and smaller and smaller every day. That's what happens, wounds heal. And as the area of this circle gets smaller, then obviously the size or the length of this radius will get smaller as well. So the length of this radius is decreasing, so getting shorter or smaller, at a rate of 0.5 millimeters per day. So every day, this radius gets smaller by 0.5 millimeters. And we want to know how fast the area is decreasing. So the area of the entire circle or wound. We're interested how fast is this entire area decreasing, specifically when the radius length is 10 millimeters. So when this radius length is 10 millimeters, how fast is the overall area decreasing or getting smaller? So how fast is the wound healing? So we know that the area of the circle or the wound is pi r squared. And because we're interested in rates of healing, so specifically here a decreasing rate, but it wouldn't matter if it was increasing or decreasing, this is all rate of change. And when we're asked about rate of change, we differentiate. So we're going to differentiate A with respect to r. So dA dr, so the derivative of A, the area with respect to r, the radius, is going to be 2 pi r. So we bring the 2 down in front, that's where the 2 comes from, and we reduce the power by 1. 2 minus 1 is 1, so it's really pi r to the power 1, which is just r. So we have 2 pi r. So this is the derivative of the area. It also happens to be the circumference of a circle. And this is the rate at which the area of the wound is changing with respect to its radius length. So this is the rate of change. The derivative of the area is the rate of change of the area. So we were asked specifically, how fast is the area decreasing, so getting smaller, at the instant when the radius length is 10 millimeters? So we're specifically interested in when the radius length is 10 millimeters. And we know that the radius length is decreasing at a rate of 0.5 millimeters per day. So the radius is getting smaller by 0.5 millimeters every day. So that means dr dt, so the rate of change of the radius with respect to time, dr dt, is equal to 0.5 millimeters per day. So we differentiate r with respect to t, that's usually what this means. So differentiating r with respect to t is 0.5, but in terms of this question, we say the rate of change of the radius, the rate of change of r with respect to time t. So we require dA dt. We're interested in the derivative of the area with respect to time. So we require dA dt, the rate of decrease of the area. So dA dt is equal to dA dr multiplied by dr dt. So let's look a bit closer at this. So we want dA dt. That's the rate of change of the area with respect to time. And we can get that by multiplying dA dr, which is the rate of change of the area with respect to the radius, by dr dt, which is the rate of change of the radius with respect to time. And the reason why we can do that is because if we were to cancel out the dr on the top and the bottom, we would be left with dA dt, which is what we have here, dA dt. So this is actually a version of the chain rule, which we had a look at in the previous slide. Now we've already worked out that dA dr is 2 pi r, so we just put 2 pi r with brackets around it. And we were told in the question that dr dt is 0.5, so we put 0.5 with brackets around it. And then we multiply out 2 pi r by 0.5. 2 multiplied by 0.5 is 1, so a half of 2 is 1. And 1 multiplied by pi r is just pi r, which is the same thing as 1 pi r. So dA dt is pi r. So the rate of change of the area with respect to time is pi r. And again, we were specifically asked when the radius length is 10 millimeters. So when r is equal to 10, dA dt is equal to pi r, which we got up here. And we swap the r for 10 with brackets. So that means we're multiplying, and pi times 10 is 10 pi. So 10 pi millimeters squared per day. So the area of the wound is decreasing or getting smaller by 10 pi millimeters squared per day. So just to go through in a bit more detail how the area, which was pi r squared, the area of the circle, differentiated and gave us 2 pi r. So if the area is pi r squared, then dA dr, the derivative of the area with respect to the radius, or with respect to r, is going to be 2 pi r squared minus 1. So we bring the 2 down in front and we reduce the power by 1. And 2 minus 1 is 1. So we get 2 pi r to the power of 1, which is 2 pi r, which happens to be the circumference of the circle. A stone is dropped from the top of a building of a height 250 meters. The distance x fallen in a time t seconds is given by x equals half gt squared, where g is equal to 9.8 meters per second squared. Air resistance is ignored. Part 1. Determine the velocity of the stone after 3 seconds. So the velocity, or speed, is the rate of change of distance with respect to time, i.e., that is, velocity is equal to dx dt. So the rate of change of x with respect to time, or t. So x is equal to a half gt squared, so that was given in the question. So dx dt is equal to gt. So let's have a look at that in more detail. So x is equal to a half gt squared, that was given in the question. To differentiate, to get dx dt, we bring the power down in front, we bring the 2 down in front, and we reduce the power by 1. Then 2 times a half is 1, and gt squared minus 1 is gt to the power of 1. And this simplifies to just gt. So dx dt is equal to gt. So we are specifically interested when t is equal to 3. So after 3 seconds, when the time is equal to 3. So dx dt is equal to gt. So we swap the t for 3. So we get dx dt equals 3g. And then we swap the g for 9.8. Because we were told in the question that g is equal to 9.8 meters per second squared. And 3 times 9.8 is 29.4 meters per second. So the velocity is 29.4 meters per second after 3 seconds. Question 2. Find the acceleration of the stone. So acceleration is the derivative of the velocity. So acceleration is the rate of change or derivative of the velocity with respect to time. So v, velocity, is equal to gt, which is equal to 9.8 t. So that was from part 1. So let's have a look where that came from. So we know acceleration is the second derivative. We were told in the question that y is equal to a half gt squared. The first derivative of this, y prime, is equal to gt. So we got that in part 1, that gt. And we know g is equal to 9.8. So gt becomes 9.8t because we swapped the g for 9.8. And next we want to differentiate 9.8t, so dv dt. So this is actually the second derivative. So if y prime, the first derivative, was gt, and we're differentiating with respect to t, then y double prime, or the second derivative, will just be g. We basically just cross off that t. And we know g is 9.8. That was given in the question. So dv dt is equal to 9.8. So the acceleration is 9.8 meters per second squared. Part 3. Show that the stone reaches the ground in 7 1/7 seconds. So if it reaches the ground, it must travel a distance or a height of 250 meters. Because remember, the stone was dropped from the top of the building, which had a height of 250 meters. So if it reaches the ground, that means it's traveled a distance or a height of 250 meters in 7 1/7 seconds. So what does that really mean? That means find t, so find the time when x is equal to 250. So this is the distance, so when the distance is equal to 250. So we let a half gt squared equal the 250. And then we solve for t, we get the t in its own. So first of all, multiplying both sides by 2 will get rid of that half. So 250 times 2 is 500. Or you could divide both sides by a half to get rid of that, which is the same thing. And we're also going to divide both sides by g to get rid of the g. So we'll end up with 500 over g. And on the left-hand side, we'll still have the t squared because we didn't get rid of them. So you could say technically you're dividing both sides by a half g. So dividing 250 by a half g will give us 500 over g. So t squared equals 500 over g. We know that g is 9.8, that was given in the question. And we bring the squared over the equal sign and it becomes square root. So t is equal to the square root of 500 over 9.8. Which gives us t equals 50 over 7, which simplifies to 7 1/7 seconds. So this is a top-heavy or an improper fraction, and as a mixed number it gives us 7 1/7 seconds. Because 50 divided by 7 is 7, remainder 1, so 1/7.